Walk through a challenge called Remote Shell. You're given both a source code and a binary. So you can see, we'll look at the source code remote shell. The actual compiled binary is a 64-bit executable, and it's running on a remote machine. It's still an active challenge. So let's look at the source code. So this is a C source code. We can see that it's using OpenSSL. And just a spoiler alert, this is actually a replicant, slight modification, well, actually a significant modification, but replicates the vulnerability that was exposed in Heartbleed. And so we just see some helper functions here, get file size, we can, the function to read a file in. These aren't necessarily important, these just provide some functionality. Down here in main is the what we're actually looking at, interested in. So we can see initially that it opens up a private key file, ID RSA, and reads it in with a OpenSSL function, closes the file, initializes some randomness, and then also reads in a public key file that we would assume that's associated with a private key, right? So now we have a public key as public key, and then RSA is the private key. And this is just raw public key, most likely in PEM format. Then we write the size of the public key of that file to standard out, and then we also write the public key. So when this program starts up, it's going to read both the private key, the public key, write the public key size to standard out, followed by the public key itself. It flushes standard out. And the next thing we do is that it allocates a buffer in malloc, right? So we've got a heap buffer, and right after that, we use that buffer to get a line up to 124 characters from standard in. And then we go into this little check. If the first 5 characters of our buffer is shell, then we execute this functionality. And it generates a random number, 64, right? And then this is shift left. And some more randomness. And we take our private RSA key and we find out its size, and we malloc that much. An additional, right? So in the heap as well, we have this encrypted challenge buffer. Okay, and then once we do that, we take our private key and we encrypt the challenge and store it in this encrypted challenge buffer with our RSA key. And there's the method that it's used, the protocol for RSA, not protocol, but the method of encryption. And then after it does that, it writes the size of the challenge and the challenge itself to standard out, flushes it. It reads from standard in the buffer. Right? It reads from standard in to the buffer, and then it also interprets that as an integer, as a long, as a 64-bit number, right? So it reads from standard in and interprets it as a 64-bit number. And if the response is equal to the initial challenge that was randomly generated for this connection, then it will give us a shell, bin bash, exec bin bash. Otherwise, authentication failed. So that's that whole functionality, right? This begins with a shell and ends with heartbeat, or ends with here, right? So the second functionality is this hbeat command. Checks the first 5 characters. If it's hbeat, then it reads in, or it looks at the first or the next buff plus 5. So right after hbeat, right, it interprets that as a size t length, which in a 64-bit binary should be a 64-bit integer. unsigned, and then it will F-write from or to standard out that much, whatever that value is, from the buffer, right, +5 plus that integer. So after the end of the integer, it'll start writing from the buffer to standard out. So you send it an H beat, you send it the amount you want it to write, and then that's it. Pretty simple functionality. So you can see that we have loaded the private key in what should be a space right next to, in our heap memory, right next to, right after where this buffer, right here, this buff is allocated. So when we are given this information spillage, where we can send an integer, a large integer, and read, we should have the private key data in our output. So here's our plan of attack. So first we need to trigger the vulnerability. Oops. Trigger the vulnerability and dump memory. We saw that. Then we need to search for a prime number in our memory dump. Once we find the memory dump, because it's just going to be a blob of memory, then we decode that n, which is our should be a prime number that was contained in the private key, and the public component of the RSA keys, right? So that was given to us. Determine Q from n. This is the next step. After we have n and we have the public key component from the public keys we know we received, then we can use RSA tool to determine n. Well, actually from n, we should be able to get n and p. Then we can use RSA tool, because this is just simple division if we have n and we have the public key components. Then we can use RSA tool with our P and a Q, and it will solve for D. And it will actually create it in a public private key format. Then we can use another script, put the new values of N, D, P, and Q, and another shell. This shell script will interact. It will send the shell command, receive the challenge, decrypt it, and send a response, and then interact remotely. So let's take a look at these scripts in order. Heartbleed, so pretty simple. It connects to a remote host, and then it receives this 8 bytes, which is going to be our public key length, and then it receives the public key. And then it's just going to write it out, and then it's going to send the hbeat command, and this is just a really big number. It's 8 bytes, right? Really big 64-bit integer. We're going to receive 2 memory pages, 8K, and write that to a file. So that's pretty simple. Find private key is going to search through our data. So it opens up the argument, which is this data file, and then it searches through it, and it actually we use Gimpy to check to see if it's private, right? Is prime, if it's a prime key. We search for all the decent size integers, and then we look for a prime one. Next, we take that output, and we use that to dump the parts of the key. right? The key type, the length, the exponent, and the n. So that's from the public key, right? So we're decoding the components of the public key. You could also do that with OpenSSL. So we have n and the public key components, right? And we have a prime number. So now we have these prime numbers, right? And we use those to solve for D. So let's first get our data dump. Python heartbleed. So we have, again, indeed 1448 of data. And then the second thing we're going to do is we're going to search, right? So Python find private on our new. Okay, so we actually found our, so it took some iterations. So it's not always there depending on the state of the process. But now we're able to dump some private keys, so dump some suspicious prime keys, and we see that one, this one right here, looks to be a prime. Indeed, if we check our previous work on this, that was 95556. Oh, that's in hex format. Yeah, right there. So that number, this B676, is the first one. That equates to this one, right? That indeed is our private key, or one of the is P, right? And so we were given. Okay. So now with P, we can give Q, right? Determine Q given N from step 3. And that would be, in Python, you could just load it and do a division. And then on decode RSA ID pub. So these two things, right? So n equals int just do the base 16. P equals int first one, base 16. Q equals n divided by P, and hex Q. All right, so 8083, and if we let's search 8083 in our shell. You can see indeed Q is that same number, right? So now we have N, we have P, and we have our Q. Q value in both decimal and hex. We can use an RSA tool. This is online. You can find it, and it will take a P and a Q and an N. In this case, we just give it P and Q, or it can take an, and it will find D. So Python on RSA tool dash P. We'll see if this works. We don't know if it does. Oops. Q. Whoops. No. So let's just get these values. I just need P actually. Okay, quit. P is this value. Q is this value. And that gives us, using P and Q, it gives us our N back. E was known, but this solves for D. So now we have D, and if we look at A alpha 77, so grep for that D, A877 shell. Maybe it's in, oh, no. D is, oh yeah, 877 shell. That is indeed. N is grep for just like the first few characters of N. And we already saw P and Q. So we do have those values loaded. And so in shell, we take our N, our E, our D, P, and Q, and we can construct an RSA key from that using N, E, and D. Is actually all the parameters we need. And we use the same RSA parameters, PKCS1 with OAEP, that makes sure the padding is correct. And so we connect. This is just a test that we can encrypt it and then decrypt it using those parameters, right? And it should be the same thing. And then we connect to our host again. We send them, or we receive our public key again, 8, right? That's the first thing we do. But then we send the shell command. We receive a length, which is actually, in this case, it's actually only 4 bytes. And our challenge, we receive that. We'll print that in hex. And then we'll decrypt that with our cipher, which is up here, right? This is our RSA cipher decrypt. And then we send that back. So send the response. And then this just goes into a loop and acts as a shell for us. Just receives data, receives whatever they have to receive, prints it to us, takes our input, and then sends it. Well, quits if we say quit. Otherwise, it will send a command to the remote host. So if we execute this, we see this was a test just to see that we could encrypt. This is our private key or public key that we received from the server. This is the response. that we send it to them, and it says that we connected and now we validated their input, and we have a shell, and we can see that we're running on a remote host with the user remote shell. And in this directory is a flag, and unfortunately this isn't the most sexy flag, but there's our flag. So that's it.